Action. The Danish physicist Hans Christian Ørsted noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass needle. He investigated this phenomenon. He found that the alignment of the needle is tangential to an imaginary circle, which has the straight wire as its center and has its plane perpendicular to the wire. It is noticeable when the current is large and the needles sufficiently close to the wire so that the Earth's magnetic field may be ignored. Reversing the direction of the current reverses the orientation of the needle. The deflection increases on increasing the current or bringing the needle closer to the wire. Iron fillings sprinkled around the wire arrange themselves in concentric circles with the wire as the center. Ørsted concluded that moving charges or currents produced a magnetic field in the surrounding space. Magnetic force. Magnetic lines of force.
The magnetic field lines leave the north pole of a magnet and enter its south pole. Each magnetic field line is directed from the north pole of a magnet to its south pole. Each field line indicates at every point on it the direction of magnetic force that would act on a north pole if it were placed at that point.
Sources and fields. Magnetic field or Lorentz force. Magnetic force on a current carrying conductor. Motion in a magnetic field. The motion of a charge moving in a magnetic field. A force on a particle does work if the force has a component along the direction of motion of the particle. Motion in a magnetic field. In motion of a charge in a magnetic field, mainly two types. They are circular motion and helical motion. Circular motion. In this type of motion, the velocity of the particle is perpendicular to magnetic field. The perpendicular force QV into B acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. The particle will describe a circle if V and B are perpendicular to each other. Helical motion. In this type of motion, the velocity has a component along B. This component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B is as before a circular one, thereby producing a helical motion. In the case of motion of a charge in a magnetic field, the magnetic force is perpendicular to the velocity of the particle. So, no work is done and no change in the magnitude of the velocity is produced. Motion in combined electric and magnetic fields. Velocity selector and cyclotron. Cyclotron. The cyclotron is a machine to accelerate charged particles or ions to high energies. This was invented by E.O. Lawrence and M.S. Livingston in 1934 to investigate nuclear structure. The cyclotron uses both electric and magnetic fields in combination to increase the energy charged particles. The particle move the most of the time inside semicircular disk like metal containers D1 and D2, which are called Ds in animation D. Inside the metal boxes, the particle is shielded and is not acted on by the electric field. The magnetic field acts on the particle and make it go round in a circular path inside a D. Every time the particle moves from one D to another, it acted upon by the electric field. The sign of electric field is changed alternately in tune with the circular motion of the particle. Each time the acceleration increases the energy of the particle, as energy increases, the radius of the circular path increases. So, the path is a spiral one. Magnetic field due to a current element. Biot-Savart law. All magnetic fields are due to currents and due to intrinsic magnetic moments of
Biot and Savart's law. According to this law, the magnetic induction dB due to an element dl of a conductor carrying an electric current L at a point such as P distant r from the element is directly proportional to the strength L of current and length dl of the element and sine of angle theta between dl and r inversely proportional to r square.
magnetic field on the axis of a circular current loop. Magnetic field on the axis of a circular loop. In this circular loop carrying steady current I, the loop is placed in the y to z plane to its center, that the origin O and has a radius r. The x-axis is the axis of the loop. We wish to calculate the magnetic field at the point P on the axis. Let x be the distance of P from the center to the loop. The magnitude dB of the magnetic field due to dl is dB is equal to mu 0 by 4 pi I dl into r by r cube is equation 1. Now r square is equal to x square plus r square. The y to z plane, whereas the displacement vector r from dl to the axial point P is in the xy plane. Thus, dB is equal to mu 0 by 4 pi I dl by x square plus r square is equation 2. Therefore, the magnetic field at P due to entire circuit loop is B is equal to B suffix x vector I is equal to mu 0 I r square by 2 into x square plus r square to the power 3 by 2 vector I. Now, we shall evaluate the magnetic field due to a circular coil along its axis. The evaluation entails summing up the effect of infinitesimal current elements, that is I d1, mentioned in the previous section, we assume that the current I is steady and that the evaluation is carried out in free space. Ampere's circuital law. There is an alternative and appealing way in which the Biot-Savart law may be expressed. Ampere's circuital law considers an open surface with a boundary. The surface has current passing through it. We consider the boundary to be made up of a number of small line elements. Consider one such element of length dl. We take the value of the tangential component of the magnetic field Bt at this element and multiply it by the length of that element dl. All such products are added together. The solenoid and the toroid. The solenoid and the toroid are two pieces of equipment which generate magnetic fields. The solenoid. In this animation, showing that the magnetic field of the solenoid, in this solenoid, the field at the interior midpoint P is uniform, strong, and along the axis of the solenoid. The field at the exterior midpoint Y, Q, is weak and moreover is along the axis of the solenoid with no perpendicular or normal component. As the solenoid is made longer, it appears like a long cylindrical metal sheet. The television uses the solenoid to generate magnetic fields needed. The synchrotron uses a combination of both to generate the high magnetic fields required. In both solenoid and toroid, we come across a situation of high symmetry where Ampere's law can be conveniently applied. The solenoid. The solenoid means that the solenoid's length is large compared to its radius. It consists of a long wire wound in the form of a helix where the neighboring turns are closely spaced. So each turn can be regarded as a circular loop. The net magnetic field in the vector sum of the fields due to all the turns. The toroid. The toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. It can be viewed as a solenoid which has been bent into a circular shape to close on itself. Force between two parallel currents. The ampere. Ampere studied the nature of this magnetic force and its dependence on the magnitude of the current, on the shape and size of the conductors, as well as the distances between the conductors. Torque on current loop magnetic dipole. Torque on a rectangular current loop in a uniform magnetic field. Circular current loop as a magnetic dipole. The magnetic dipole moment of a revolving electron. The moving coil galvanometer. The galvanometer consists of a coil with many turns free to rotate about a fixed axis in a uniform radial magnetic field. There is a cylindrical soft iron core which not only makes the field radial but also increases the strength of the magnetic field. The galvanometer used as a detector to check if a current is flowing in the circuit. In this usage, the neutral position of the pointer is in the middle of the scale and not at the left end. Depending on the direction of the current, the pointer direction is either to the right or the left. The galvanometer cannot be used as an ammeter to measure the value of the current in a given circuit. This is also used as a voltmeter to measure the voltage across a given section of the circuit.